Alrighty, we're in chapter 4. Questions on any of the concepts, any homework problems, anything like that? I just made some more videos for homework problems from 4.4, but I ran into a slight, I didn't really have time to get them all uploaded or anything yet, but ran into a slight difficulty in that I just got a new tablet to work with, and I plugged it into this machine to see how it would do, and the machine didn't seem to recognize the files in it. No big deal. So I did the videos on my older tablet and went to upload them though, and this wasn't opening the old tablet anymore after it tried to open the new tablet. So I've got to figure out what's going on there. But okay, technology woes. Questions? Any questions? No? All right. So the big idea really in this chapter is the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus. And it must be pretty important, I guess, if it's called the fundamental theorem. And it's really, quite an amazing thing. And I think it's interesting that, in a Calculus 1 class now, that plenty of people in, the U.S. and other countries, everywhere, they may take it in high school, right, nowadays. Well, and by chapter 4, and actually, we could have done it in chapter 3, so to speak. I mean, we learned derivatives, and then we could have gone straight to something like chapter 4. So in the first half of a class, you could get this idea of derivatives, get this idea of definite integrals, and put the two together in the fundamental theorem of calculus. But it really wasn't that long ago that mathematicians didn't realize these two things were connected. So they did definite integrals, they did derivatives, but they didn't know that you could put them together with this fundamental theorem of calculus. And so this is a pretty big deal, and in the history of the world in mathematics and so forth, it's a relatively new thing. And we're talking, what are we in now, 2000, so 300 years. All in all, that's pretty recent. And so in that fundamental theorem of calculus, it says, if we let f of x equal f prime of x on, some closed interval AB, and f of x is continuous. Now, it actually doesn't have to be. And we even might look at some things like that. But, usually when it's first introduced, we say the function's continuous. Actually, all you really need is continuous except at a countable number of places. Countable. Well, so that could be infinite, but it would line up with the integers, like 1, 2, 3, 4, the counting numbers really, so countable, 1, 2, 3, 4. And so, even if your function's got a few discontinuities in it, 3 or 4 or something like that over the interval, no big deal. We can still use this theorem and get answers as long as we can do our antiderivative stuff. So f is continuous, f of x is continuous, then this definite integral from a to b of f of x dx, which you could write uppercase F prime in there. It's just often they do this, many books and so forth will say it this way. This is just f at b minus f at a, so the antiderivative. So it turns out this idea of a summation, a limit of a summation, this infinite limit that we have, we can evaluate that for a given function simply by knowing its antiderivative. And when you start thinking about that, that's a big, big deal. I mean, that's amazing. That, if we want to add up a bunch of pieces of a function, and again, intuitively, think of it as an area, then we can get that simply by looking at the change in the antiderivative. Okay, so there's our fundamental theorem of calculus, and so if I would like to find the antiderivative from 1 to 2 of x squared dx, this says all I have to do is do the antiderivative of x squared, so x cubed over 3. So this is one reason antiderivatives are so important. And then evaluate that from 1 to 3. And so that is a lot of 3's here. 3 cubed over 3 minus 1 cubed over 3. And so that's just 3 squared, so I get 9 minus 1/3. So that's 27 thirds minus a third, so 26 over 3. And just like that, I've done that definite integral. I don't see any limits happening or any, I don't notice them. They're all under there, under the hood, as you might say. But yeah, we just really don't notice. We just have to be able to do antiderivatives. And there's the key. So to do this calculation, at least symbolically, as I did it here, we just have to be able to do antiderivatives, which is not necessarily an easy thing, but that's it. That's our task, right, is to do these antiderivatives. Now, some other aspects of this fundamental theorem that I think we want to definitely point out, bring attention to. One is the second fundamental theorem of calculus. Okay? Now notice, see, this is a lot like World War I, World War II, or the Battle of Bull Run and the Second Battle of Bull Run. That World War I was not referred to, at least in the U.S. and probably anywhere, as World War I, right? Because we had it and everybody thought, oh, glad that's over. Hope we don't have another one of those, right? So you wouldn't have called it World War I. That's like the fundamental theorem of calculus, right? Nowadays we say World War I in the U.S. anyway. I don't know about other places. But there are also things like the Battle of Bull Run, Teddy Roosevelt thing. But we don't tend to refer to the first one as the first battle. It's just the Battle of Bull Run. And many people, if you were to find them. Nowadays, they'd be hard to find, but certainly when I was growing up, I knew people who talked about the Great War and World War II. Okay, so, it was, it's the same thing. We could have the first fundamental theorem of calculus and the second fundamental theorem of calculus, but we have the fundamental theorem of calculus and the second fundamental theorem of calculus. Okay, and here, theorem, might need that word in there, theorem of calculus. And here, the idea is actually in some ways pretty simple. It just says, if instead of telling you what this upper limit is, I just made that a variable. Okay, I said, well, it could be anything. Well, then, actually, this becomes a function, right? Because if I could define a function f of x like this by saying, well, I want a definite integral from a constant a up to some variable x. And now, here, since I have an x there, you don't tend to put an x here. That gets confusing, right? Because really, this is sort of a dummy variable situation. I need these things to match, but I really don't care what they are. I don't care if they're x or z or w. And so oftentimes you'll maybe see something like that. Our textbook would do that. Okay, so we can define a function like this. And then, if I want f prime of x, it is just f of x. It's that easy to take that derivative. Okay? And, well, of course, right? Because the fundamental theorem of calculus says, how do I do this? Well, I find the antiderivative of that function. And I evaluate it at x, and I subtract it, evaluate it at a. Well, okay. So then when I take its derivative, well, I have the antiderivative here in terms of x. Take its derivative. Well, the derivative of the antiderivative is back to the derivative. All right, so, I went from little f to some other function. Now, I can call it big F here, but you got to be a little bit careful. So I get that antiderivative, I take its derivative, I take the answer to this thing, and I get that. I have to, because that's the way these things are made. And so that derivative is that simple. But it's again one of these things that as students you often just sort of forget this. I mean, maybe in a problem they would like you to use something like this, and you just forget. Okay. Now, with let's mess with some notation here just to kind of see this. Is because I really don't like using the uppercase F to kind of show what's going on. So what we're going to do is we're going to say, let's let our f of x here, uppercase f of x, equal our antiderivative from a to x of g of t dt, just so I've got a different name. right, then our fundamental theorem of calculus would say that the answer to this is uppercase G of x minus uppercase G of a. That's a constant. This is a function, okay? But this is where, right, we have that G prime of x is equal to little g of x. And so there's our function, uppercase f of x. Well, now take its derivative. That's g prime of x minus 0, because again, that was a constant, so I get 0. But uppercase g prime of x is just whatever that thing was in there. Little g of x. And so that's exactly what's going on here. Okay, so it's sort of that simple. It's like the idea of squaring something and then taking its square root. Actually, a better way to go would be its square root and then squaring it. Because I actually can't write. If I square something first and then take its square root, I might actually not get the same thing back. Because if I square a negative number, I get a positive. Take its square root, that's a positive. But the idea, right, is that if I do something and then undo it. So here, I did something, essentially I did an antiderivative, and then I undid it. So I get back to where I started. Okay, second fundamental theorem of calculus. Questions on anything on this stuff? No? Okay. And I think, let's see, second fundamental, where is, isn't average value in here somewhere? In this? Yes, okay, it's also in 4.4. So average value, then, let's look at that. So average value of some function f of x on AB. Now, there are a couple ways to look at this that I think seem very reasonable. Now, this works whether f of x is positive or negative or whatever, but it's probably easiest to get the intuition from a positive function. And so when you think about this average value of f of x, so it's defined as an integral from a to b of f of x dx divided by that length b minus a. Now, here is where this notion of thinking of an integral as area and so forth really helps a lot. So again, that integral is not defined by area. However, thinking of it, interpreting it as finding an area can be very helpful. And so if you think about the picture of this for some function, there's my function f of x, and what I've done with the numerator is I found that area. Okay, that's a great way to interpret what I've just done. So that's the numerator. Okay, so now I have an area, but let's think about area, right? Area is just some length times width. or height times width, I guess, as you're looking at it on the board here, or something like that. Well, so suppose I tell you that the width is b minus a. Then what's the length, or height? Well, length then is my area divided by b minus a. Okay, so the numerator is my area. Then I'm dividing by the width here, right? So I've got this area divided by the width. Well, that gives me a length or a height of a rectangular area. And so what this calculation has done, because this goes from A to B, is it has determined the height of a rectangle there's L. It's determined the height of a rectangle that has the same area as A there. And when you think about that, just sort of looking at it that way, that seems like a relatively decent definition of the average value of a function. Right? Is just take, oh, what's the area under there? Divide by that width, and you come up with a number that if I had a constant function, I would get exactly the same area. Seems reasonable. Okay, so that's one way to look at this idea of average value of a function, just sort of from, oh yeah, a rectangular area. Okay, now, in essence though, then another way to think about it is I found a height, and of course my height's probably much taller than this. You have to maybe like squint your eyes and turn your head or something like that to make this look like it's in scale, because what should happen, right, is the area up here should fit right there. Okay, to make that work, right? I should be able to cut that off. If it was Play-Doh or something like that that I could mold around, I could cut that off and just stick it right there and make that triangle. But think about that. Isn't that what you do when you find an average of stuff? Right? So if I'm just, get rid of that part right there. If I said I have, I don't know, it's cold out maybe at some point, and I've stacked snowballs, because that I could do. If they were marbles, I'd be pretty impressed if I could do that. So, so I've got some snowballs matched up there. And if one were to ask, well, what's my average number of snowballs in a stack? One way to look at answering that is to physically move the snowballs so that every stack has the same number. And so, you know, I could move that there, and now they each have 3, and oh, yeah, well, I'll call that the average. Well, yes, that is what the average is. And how could I get that number, right? Oh, I take 4 here, plus 2, plus 3, right? And so I'm adding up the total. Well, that's really what an integral does. It's adding up a total sum. And then I'm dividing by n. Now, you know, here it gets a little harder to talk about width of an interval or something, but, you know, I could say, you know, there's 1, there's 2, there's 3, like that, and they're that wide, and so I'm dividing by that width, 3. And that's how I would determine that, oh yeah, the right answer is 3. Okay, so really, this, because all it's really doing is adding up that function value at all those spots along the way, that's when you take the limit anyway, that's what it's doing. It's adding up an infinite number of these function values, but the width is really tiny, right? So it's really just this idea, but adding an infinite number of snowball stacks and sort of pushing them together so they're all touching and all that. So, that's all an average value is doing. And when you start to think about it that way, yeah, it's not really a mysterious definition at all. I think it makes a lot of sense, kind of looking at these things those two different ways, both as adding something up and dividing by the number that are there to get a constant height on everything. Oh yeah, constant height. That's what we're trying to do. Or just to say, well, okay, I just want to find a rectangle that has exactly the same area as under that curve. Sure, I can do that. Okay, so that's average value. Questions on that? Anything about that? No? Okay, so those are the big ideas from the fundamental theorem of calculus. And then, once we have that fundamental theorem, as I said, the trick is antiderivatives. Okay, and there you go. That becomes the hard part. And if I can't find an antiderivative, I am stuck as far as trying to use the fundamental theorem of calculus. Okay, so in 4.5, they give us a technique, and they mention integration by substitution. Now, we've actually been given an earlier technique, and we'll come back to that. Let's go ahead and talk about integration by substitution. The idea here is to undo the chain rule. Okay, you're simply trying to undo the chain rule. If we can undo the chain rule in something, then we might do a better job of doing the antiderivative. Okay, so if you see something like, suppose I want to do, and whether we do a definite integral or an indefinite integral antiderivative, the key in 4.5, or the question, is all about the antiderivative. I mean, that's the step. Because after 4.4, hopefully we get the idea that, oh, I want to do a definite integral, you supply me with the antiderivative, I'm all set. At least if I have a calculator or something, right? Because then I can, or if nothing else, you give me the antiderivative, I'll plug the two numbers in and then leave it that way and say, there you go. If you need more, simplify it yourself, darn it. Right? So that's the challenge, is the antiderivative. And so if you have something like this, okay, that's this idea of integration by substitution, is we're looking to be able to do problems like that. And the key is, if you know your derivatives really well and you've practiced lots of chain rule derivatives, then something like this, you might not really even need this technique. Okay, because, right, I look at that and I say, well, okay, if I want that thing's antiderivative, I need to think of what I took the derivative of to get it. And if I think about it for a minute, If I take the derivative of sine 2x with respect to x, I will definitely get a cosine of 2x. Except I'm not done yet, right, with the derivative, because I need the chain rule. I need the derivative of what's inside there. And so I'll get cosine of 2x times 2. And so I would write that as 2 cosine of 2x. So see, I can look at this and say, oh, it's almost what I need. Okay. But again, the key here is I know some things about definite integrals and antiderivatives and so forth, is that constants can flow in and out of this darn thing easily, right? I can put a constant here or out there, and it's the same thing. Ah, well, so that's where we get fancy, and we would say, you know, this is sort of a guess and check method. But I look at that and I say, oh, well, that's what I need. So that's what I'm going to use. I'm just going to use 2 cos. I'm going to solve that problem instead. Well, except that if I want them to be equal to each other, what I can do is, okay, I need a 2 cosine, well, put that there, cosine of 2x. I need that, and then I know the answer. But those aren't equal. Not even on a Tuesday. Okay, so we can't do that, except, right, it's our lovely math trick of doing things like multiplying by 1 or adding 0 is, oh, well, if I multiply by 2, just divide by 2. Now it's the same. Okay, so these are one and the same. And, well, wait, I don't know how to do that one. Okay, because, well, I didn't know how to do that one. I don't know how to do that one. Except if I pull the 1/2 out and write it this way, now I know how to do it. Okay, that I can do because I just did it over here. Right? I took the derivative sine of 2x. I got 2 cosine 2x. So I know the antiderivative of that. And so finally, I can write 1/2 sine of 2x and then plus my arbitrary constant. Okay, so that's what we're trying to do with this method. Now, it's one of those things that for simpler things, and this is probably about as simple as we can make it, for simpler things, I can pretty much do a guess and check method. And that's what I tend to do. I mean, you know, I've been doing this a long time. I know my derivatives and antiderivatives pretty well. In essence, this is how I would do this problem. Okay. Now, if I just wrote it down, it wouldn't look quite like this because, again, I would do a lot of this in my head and just come up with the answer. Okay. So I'm doing all this, but you wouldn't see it. But sometimes it gets harder, or sometimes, you know, stuff like this is just in the middle of something bigger, and you don't want to mess it up. And so, you know, we want a technique that will work well. Now, this we have to talk about this thing, a differential again, is that if we have something like, you know, f of x and f prime of x is equal to f of x, little f of x, like that, right, then we would write this differential idea, sort of the small change in f, big F, with that small change in x, we would write df equals little f of x, or big F prime of x, dx. Okay, and again, that is just that idea that if I take a slope times a change in x, I get the change in y. Okay, slope times a change in x gives me a change in y. And so we're going to use that idea. In notation, we could write something, if we know this is true, we can write this. The antiderivative of f of x dx, that is exactly the same thing as the antiderivative of df, where f is the uppercase F. Now, it has to be true. Well, why? Because they're equal. They're the same thing, they're just a different name. Okay? Nickname, maybe. Or maybe that's the nickname, or something like that. But they are the exact same function of x. Okay? So if I want an antiderivative of that function, well, it better be the same as the antiderivative of this function, at least up to an arbitrary constant. But typically, when we leave the antiderivative signs there, we don't toss in the arbitrary constant. Okay, so those are one and the same. So as we look at our problem here, what we would have is that if we said f of x is the sine of 2x, then our little f of x would be 2 cosine of 2x. And so by this idea, right, we would have that the antiderivative of 2 cosine of 2x dx is equal to, and here I'm just going to write it as f, oops, sorry, wrong way, df, there we go. It's the antiderivative of df, because that is our f, big F prime, or little f of x times dx. Now, the key here is that when we do these sorts of substitutions, what we end up with here is going to be much easier to deal with. Now, it's not quite as clean as this. This looks really clean, but not quite. But what we do with this, our technique, okay, when we're given something like this, to find the antiderivative of, okay, and that's, notice, we've got that here. We've got the cosine is f, and the 2x is the g. So when we've got something like that, we're going to use kind of this idea of differentials, but actually, we're going to use it in here. Okay, we're going to mess with this in here. So this idea of differentials, if we let u equal, oops, well, yeah, let me leave it like that for a moment. If we let u equal g of x, then du is equal to g prime of x dx. Okay, so if you see something like this, what you need to hope for is that what you're actually trying to do, the real problem you're trying to do is that you have this. Okay, because now if I have that, so if I see something that I think looks like this, I'm going to try to make this kind of a substitution. Now, it's only going to work if I've got that there. And so, by doing that though, using that substitution, this becomes f of u. And this part is du. And the idea is, oh, I know how to do this because it's one of my basic simple functions. Okay? Now, if I don't know how to do this, well, I'm out of luck anyway. Okay? But if I know how to do this, then I'm fine. Now, we'll see it here. Let's do our problem again, our cosine 2x, and kind of see that, well, sometimes it's not there, but we can end up making it be there. Okay? So we may or may not be able to. It depends. But so, you know, we were looking at cosine of 2x dx. And so here I see this and I say, oh, well, let's let u equal 2x. And then my du is 2 dx. Okay, so I just take the derivative. Typically it's something not too bad. That's the idea. And so I want to rewrite this then, you know, in terms of just the u. But again, the problem is, oh, well, I don't have g prime g prime of x with the dx. I just have dx. Oh, this is a case, though, where tossing in that 2 is not a problem. And so I rewrite this as my 1/2. Well, and actually you might want to write it this way, 2x and then 2 dx. All right, so there is my cosine of u, and there is my du. And so this becomes 1/2 the antiderivative of cosine of u du. And that, as I say, I can do that one. Okay, so this is just a method to kind of get everything right the first time, right? To plug it all in. And so then, oh, my antiderivative of the sine, the cosine is the sine. So this is 1/2 sine of u plus an arbitrary constant. But now, I didn't ask for the antiderivative in terms of u. I asked for the antiderivative in terms of x. See, once again, it's not all about you. Hey. So equals 1/2 sine, and I just substitute that back in, 2x, and then plus my constant. And I have that. But so that's the game, is looking for a composition, looking at the inside of that composition, and hoping that the derivative of that inside is there, or you can make it. Now, the problem, you know, here we got lucky because that derivative was just a constant. So it's easy to slip constants in and out. Not a problem. But, you know, if it had been something involving x, we might have been stuck and not been able to use substitution. So that derivative needs to be there. And let's see. Well, they give, let's go for one of their easier ones. So, for instance, their example 4, in their case, they would just like that antiderivative of the square root of 2x minus 1 dx. Okay, so I look at that and I see, oh, there's the function 2x minus 1 inside the function square root. And so that is probably, you know, I would go with whatever that inside function is, u equal 2x minus 1. And then I take the derivative and do the du thing. So du is 2 and dx. So again, you know, we're faced with the 2 dx isn't there, okay, but we can make it. And same way we did before. So, so what we have is this antiderivative, square root of 2x minus 1 dx, can be rewritten in terms of u as the 1/2 the antiderivative of the square root of u and du. So I just kind of jumped over that step of putting in the 2 in front of the dx and the 1/2 out in front. Okay, so we can rewrite it that way. Now that's 1/2 u to the 1/2 du, that antiderivative. And so now I have 1/2 u to the 1/2 plus 1 is 3/2, and then divided by that 3/2, plus my arbitrary constant. And so now I can do some simplification and put my 2x minus 1 back in there. So let's see, invert and multiply, so I'll get 2/3 times 1/2, that's 1/3. So I'll have 1/3, and then 2x minus 1 to the 3/2 plus c. Okay, any questions on that? Now, you don't have to change that problem a lot to have trouble, you know, where you can't use the integration by substitution. So, for instance, you know, so here's actually, I think they, it's their example 5, and well, I say you can't. They end up doing some, we don't have time, but they end up doing some fancy things. But in example 5, they have something that looks like it wouldn't work. Okay, because I look at the inside part, and I would say, oh, u is x minus 1, so du is just 1 times dx or dx. Well, I can do that substitution just fine, except I've got a u sitting around. I mean, sorry, an x sitting around. What now? Well, this is a case where you can do something with this, is that once you decide on this substitution, there's nothing wrong with then pointing out that that also means x is equal to u plus 1. And so I'll just go so far here as to write this so you could write this as u plus 1 times the square root of u du, and that, if I multiply it through, I can do it. Okay, now, on the other hand, so here's sort of an example 4 prime, kind of like a derivative problem. And so if I had 2x squared minus 1 dx, at least with this sort of substitution, we're stuck. Now, actually, I'm pretty sure we can still do this with a different substitution. But if we go with what we know at this point, we're pretty stuck with this, right? Because I would say, oh, let u equal 2x squared minus 1, and then du is 4x dx. And that would cause me problems, right? Because I could put the 4 in and take it out, right? I could put 4 and a 1/4, not a problem. But if I put in an x, I have to divide by x. Well, the x can't come out of there. And so you might get stuck here. Like I say, actually, I think we can do this just fine. It's beyond what we tend to ask in a class like this. So, second semester, you look at this one and look at substitution techniques. So it's still a substitution, but it is not so straightforward as these. Okay, trying to think. I think you substitute something like arc sine, arc tangent. I don't know, one of those. I'd have to think about it. But it can be done, but we would be stumped in this class, okay, because we wouldn't know what to do with that darn x that's hanging around. Okay? All right. Today's Thursday, so yeah, I'll see you on Monday. I'll keep feverishly trying to work on getting caught up on some things, and if you have any questions on anything, just let me know.